Lecture number 14, Colligative Properties. So we're going to continue our discussion about these solutions and talk about some special properties or characteristics that change the liquid phase or have an effect on the liquid phase as we make a solution, these colligative properties. So one thing to remember for these colligative properties is that they all depend on the number of solute molecules, not necessarily their identity. So the fact that we form the solution is going to depend on the intermolecular forces. But once that solution is formed, the number of solute particles is going to have an effect on these colligative properties. Right? So we're going to predict then the number of particles based on whether these solutes are electrolytes or non-electrolytes. So if we remember back previously, we can talk about electrolyte as something that dissociates when we put it into the solution. So if we're making aqueous solutions, if we dissociate completely, that is going to be what we call a strong electrolyte. Right? So like sodium chloride is a strong electrolyte. Once you put sodium chloride in water, it completely breaks up to the sodium ion and the chlorine ion. Right? We can also remember the weak electrolytes, those things that dissociate only a little bit. So if we put like acetic acid into water, part of that acetic acid forms the acetate ion, part of it forms the H+, but a portion of it stays together as the acetic acid compound. Right? This would be in a weak electrolyte. So we're going to end up not forming as many ions, as opposed to this non-electrolyte, which is going to form no ions in solution. Something like glucose. When it dissolves, it stays together. We just have that one single glucose molecule. Right? So the number of solute molecules is going to be directly related to whether it's a strong electrolyte, weak electrolyte, or non-electrolyte. And we will see later at the end how this idea of the total number of particles plays an effect. Our initial look at these different colligative properties is just going to be very generic, and we're not going to too much worry about the number of particles necessarily. We're going to look at some sort of a concentration unit and different. So the first one we're going to look at is this vapor pressure lowering. Right? So the vapor pressure lowering, the non-volatile electrolyte, if we put a solution or a solute in with our solvent, it's going to lower the total vapor pressure of that pure solvent. And this is going to occur versus Raoult's law, which says that the vapor pressure of the solvent above the solution is proportional to the mole fraction of the solvent present. So the pressure of the solvent, the partial pressure of the solvent, is going to be the mole fraction of the solvent times the initial, or the partial pressure when it was only solvent. It is P naught. So this is going to be proportional then to the mole fraction of the solute present. So the change in vapor pressure is going to be related to the mole fraction of the solute times the vapor pressure of this solvent. Right? So we can calculate the new vapor pressure by looking at the top equation, or we can talk about the change in vapor pressure depending on the amount of solute we put in there, the mole fraction of the solute. So the more mole fraction, the larger the mole fraction is, the more solute we put in, the more we're going to change this vapor pressure. And we can think about it in this way. If we look at these excuse me, two figures, the vapor pressure is just the number of those molecules that are able to escape the liquid phase into the gas, right? Which is going to be a function of how many, sort of the size, the number of molecules that have the probability of escaping them. If we have this solution, especially a non-volatile solvent, or solute, then that's going to decrease the total number of molecules that are at the surface that can come out. Right? Which makes sense. If there's fewer molecules that can come out, fewer molecules are going to come out of the solution, therefore the vapor pressure should go down. Right? For these non-volatile solutions. And if we put another volatile, we're just going to have the pressure will be changed slightly, but it will be a function of the vapor pressure of this new volatile compound. So typically when we talk about this lowering of vapor pressure, we're talking about putting a non-volatile solute in there. So if we're go back to our sodium chloride example, the sodium chloride isn't going to escape to form sodium vapor, just the water molecule. So that would be an example of a non-volatile change. So the presence of these additional solute molecules is lowering the vapor pressure because fewer molecules can escape. The next colligative property that we're going to talk about is this boiling point elevation. So a solution will always boil at a higher temperature than the pure solvent. This is the colligative property usually is a result of the vapor pressure lowering. Right? Since the vapor pressure, when the vapor pressure equals the boiling point, we are going to get boiling. So if we're lowering the vapor pressure, it's going to take longer for us to get to that energy. And this boiling point elevation is proportional to the molality of the solution. So the change in boiling point, or temperature of boiling, is going to equal some K value, this proportionality constant based on the solvent, times the molality of that solution. We'll see a similar thing when we talk about freezing point. A solution will always freeze at lower temperature than a pure solvent, which is why we put salt on for ice sidewalks, because we're lowering the freezing point of that solution. And again, this freezing point is always going to be proportional to the molality of the solution. So the change in temperature of freezing is going to be equal to, again, now this proportionality constant for freezing, times the molality of that solution. Right? So the Kf is Kf, and then the Kb are going to be related to that species, that single species. So it's based on the solvent. The molality is for the solute. Right, so we can see here, if we look at this figure, here's a whole bunch of different solvents and their respective boiling points, melting points, and their K values for either Kb or Kf. And we can see that they vary widely. Again, these are a constant, so you'll be given those, or that you have to determine them. So you'll either be given or you'll have to solve for them. But in general, we have this, that we're always going to get boiling point elevation and freezing point depression. So if we look at our phase diagram for water, once we add, so the pure solvent is the solid line, and a solution is the dotted line. So it's bringing the fusion point that down, right? We're lowering the point of melting, right? So that freezing point is being depressed, it's going down. So if we look at the normal freezing point of the pure solvent versus the freezing point of this solution, we see that it occurs at a lower temperature. If we look at the boiling, we've now elevated the boiling. So again, the normal boiling point between the pure solvent and the solution is occurring, the solution is occurring at a higher boiling point, which is essentially causing that line to move sort of down, if you will, overall. Right. So those are sort of three of the colligative properties. The freezing point, depression, boiling point elevation are sort of related. They have a very similar process. And then we have vapor pressure lowering. The next one is this osmotic pressure, which you're probably more familiar with taking biology. It's the osmosis is the movement of a solute particle from a region of high concentration to a region of lower concentration through some sort of a semi-permeable membrane, right? And it's the solvent that is moving, not the solute. So we are taking, this solvent is moving from a more dilute solution to a more concentrated one. So we are moving some of those solute molecules from the less concentrated into the more concentrated to lower that concentration. The osmotic pressure can be applied to prevent the flow of solvent. So that's how we measure it. It's the pressure we need to add to create this from happening, this flow of solvent from happening. And it can be calculated using this equation where the osmotic pressure is equal to the molarity now, the molarity of the solution, times our gas constant, times the temperature in Kelvin. So now those four sort of colligative properties, we should be able to calculate them fairly simply based on the equations that we have. So let's talk about the volatile non-electrolyte solutions. So for a volatile non-electrolyte, something that can be vaporized but is not an electrolyte, the solution can contain both the solute and solvent. Right? For each volatile component, it's going to lower the vapor pressure of another one, which will, because of the mole fraction, so it's going to be related there. So the vapor pressure for the higher mole fraction of a more volatile, so the vapor will have a higher mole fraction of a more volatile compound. So we need to take into account these mixtures. We'll look at the different vapor, which one's the more volatile, and the most volatile is going to have the higher vapor pressure, but the overall vapor pressure is still going to be lower than any of the pure volatile compounds themselves. So for all of these colligative properties, we've talked about how we can calculate them based on this molality or molarity. For these strong electrolyte solutions, when they break apart, they're going to break apart into various ions. So we have to relate the number of particles that are present using what we call the Van Hoff factor, which is going to be related to how many ions we get when they form a solution. Right? So for example, go back to our sodium chloride. When sodium chloride dissolves in water, we're going to get 2 ions out of that. So its Van Hoff factor, the highest value that it can have is 2. And then we can see that we can get deviations from that based on ionic strength. But ideally, our Van Hoff factor for sodium chloride would be 2. For something like trying to think of something that has 3 particles. Magnesium chloride, where would be MgCl2, again is soluble, so they would have a Van Hoff factor of 3. So if we include this Van Hoff factor to those colligative properties, what we're going to do is just include that value for I in front of them. So the change in vapor pressure is going to be the delta P is equal to this Van Hoff factor times the mole fraction of the solute times the vapor pressure of the pure solvent. For the boiling point elevation, it's going to be the change in boiling point is going to be this Van Hoff factor I times the Kb times the molality M. Same with the other 2. So this Van Hoff factor is accounting for the fact that for these strong electrolyte solutions, we're not going to have 1 particle, but we're going to have multiple based on the fact that they break apart into their ions. And so we're going to do some calculations and do some predictions based on these.
Dad, I done did it.